Let's look at similarity transformations. So a similarity transformation is a dilation or combination of transformations plus a dilation. So two figures on a plane are similar if one can be obtained from the other by a dilation or a sequence of rotations, reflections, translations plus a dilation. So we can have a congruence transformation along with our dilation, and that would still be a similarity transformation, so long as we have a dilation. Because the rotation, reflection, translation isn't going to change the size at all. But if we perform a dilation, then we are going to change the size, but not the shape. So we'll have similar figures instead of congruent figures. Below, triangle ABC is similar to triangle A prime, B prime, C prime, as shown by the intersecting rays. If we have values on a coordinate grid, we can compare corresponding sides to find the scale factor. If the scale factor is consistent for all pairs of corresponding sides, then the figures are similar. So here we can see that if we draw a ray from our point of dilation through the original, it will land on the corresponding point on the image. Okay, so this is a similarity transformation. This would be a dilation. We're going to look at dilations on a coordinate plane. Okay, so here's the first one. And this one is in your notes. We're going to use the definition of similarity in terms of similarity transformations to determine whether the two figures are similar and explain your answer. So triangle JKL and triangle MNP have different angle measurements. Since similarity transformations preserve angle measure, there's no sequence of similarity transformations that will map triangle JKL to triangle MNP. Let's see if they really have some different angle measures. Okay, so you shouldn't just necessarily just look at the figure and say, oh, the angles aren't the same. You can prove it by finding the slope. So for instance, here, if we find the slope of JL, right, so J goes down 2, I go down 2, 1, 2, and I go to the right 1, 2, 3. So that would be a slope of negative 2/3. MP is the corresponding point, right? And by the way, you can tell by how the letters are listed. So JL, MP. So if we find the slope of MP, that should be, if these are similar figures, that should be the same. Now, if we're going to have congruent angles, the sides have to meet each other at the same slope. So the slope of MP is negative 2. Right? It goes down 2 to the right 1. Well, negative 2 is not equal to negative 2/3. So because we have different slope measurements, those angles are not congruent. And therefore, triangle JKL is not similar to triangle MNP. Right, so you can map triangle RST to triangle XYZ by the dilation that has the coordinate notation. So we have to identify our dilation, we have to identify the scale factor. Because when we write a dilation, it's going to be written D for dilation, and we're going to have K, X, K, Y, where K is the scale factor. Right, so we have to find our scale factor. Let's use a pair of corresponding points and find the scale factor, and then we'll check it by seeing if we multiply the original coordinates by the scale factor if we get the image. Right? So we're mapping triangle RST to XYZ. RST is going to be our original. It's a little bit hard, or pre-image. It's a little hard to know who's the original when they don't have prime marks. The prime marks makes it easy, unless it's really clear who's the pre-image and who's the image. But let's assume that RST is the pre-image and XYZ is the image. Okay? So to find our scale factor, it's kind of right up here. Our scale factor is going to be a measurement from the image over the corresponding measurement from the pre-image or the original. Right, so ST is going to be the pre-image, XY or ZY corresponds with that segment. Right, so this is an easy segment to use because it's horizontal. Right, so the image is XYZ is the larger one there. I wrote down the coordinates. So z is located at -3, 3, -3, -3, and y is located at 3, -3. So -3 and 3 are 6 apart. So that measurement of that segment is 6. The corresponding segment is TS, and TS is 2. Therefore, our scale factor is 3. Let's check and see if that works. Okay? So if I multiply 3 by 0, 1, I get 0, 3, right? And 3 times 1 is 3, and 3 times -1 is -3. Okay, so if I multiply s by the scale factor, I get y. How about if I multiply t? Well, 3 times -1 is -3, 3 times -1 is -3. That works out for all my points. So you can check it mentally. You don't have to necessarily match up each pair of corresponding corresponding sides when it's on a coordinate plane. You could double check once you find your scale factor that if you multiplied your pre-image points by that scale factor, do you get your image? Okay? That's kind of easier than trying to find the scale factor on those diagonal lines. So now we know our scale factor is 3, which means the notation is going to be a dilation 3x, so our x's are 3 times larger, and our y's are 3 times larger, and we're done. Oh, almost done. A dilation is a similarity transformation. Therefore, we need to write in our similarities statement. We have triangle RST is similar to triangle XYZ. Right, and now we have one more. You can map ABCD to EFGH by the dilation that has the coordinate notation, followed by the reflection that has the coordinate notation. All right, so we need our dilation, we need our scale factor, and then we need to figure out what other transformation. Again, you want to match up corresponding parts. So we can see by how it's written that AB goes with EF, and that would be a good one to choose because it's a vertical line. Also, AD and EH would be perfectly good. Either one of those is just fine. Let's use AB, which is 2, and EF, which is 1, 2, 3, 4. Okay. So ABCD is going to be our pre-image, and EFGH is going to be the image. So to find the scale factor, we'll take the pre-image, which is 2, because we're using AB, over the image, which is EF, which is 4, and, oh, excuse me. Whoops. I just said image over pre-image. Let me make sure we put in the right numbers. So EF is our image. EF is going to go in the numerator. AB is our original, is our pre-image. That's going to go in the denominator. I think I'm getting tired. All right, so EF is 4. AB is 2. That's going to give us a scale factor of 2. Okay. So we want to make sure once we've identified our image, and in this one, the way it's written, we're going to make the second one the image and the first one the pre-image. We need to make sure that's the way it goes in our scale factor. So the dilation would be d2x to y. Just multiply your x's by 2, you multiply your y's by 2. Okay. And we could check that out and make sure that worked for all our coordinates, right? Maybe we should. All right, just make sure we're correct here, right? So A is at 0, 0. B is at 0, 2. C is at 2, 1. And D is at 2, 0. Boy, that's crooked. And then E is also at 0, 0. F is at 0, -4. And G is at 4, -2. And we have one more coordinate. We have, I'll just stick it over here. We have H, who's at 4, 0. Now ignore the signs for now because we have one other transformation that's going to change the signs. So don't look at the signs, just look at the values. So if we multiply 0, 0 by 2, we're going to get 0, 0. If we multiply 0, 2 by 2, we're going to get 0, 4. If we multiply 2, 1 by 2, we'll get 4, 2. And if we multiply 2, 0 by 2, we'll get 4, 0. So you can see that if we multiplied our pre-image points by their scale factor, we would get our image points, except for the sign, because the next sign is going to change it. We have a reflection that has the coordinate notation. So a couple ways you can write that. We are reflecting over the x-axis. And I'm going to put reflection over the x-axis. And there's a way we can write in coordinate notation as well that shows what's happening. Okay, so reflection over the x-axis in coordinate notation is we have the reflection and so it doesn't get confused with rotation. I'll write the word reflect. And it's actually, we don't really need the word reflection. I'm going to leave that off. XY goes to, and what happens when we reflect over the x-axis? X stays the same, y becomes the opposite. So here's how you can write it without even using the word reflection by showing what happens. So you can write reflection over the x-axis, but in coordinate notation, that would be xy goes to x negative y. Because the x is going to stay the same, but the y will be the opposite. Dilations and reflections are similarity transformations, right? So dilation's similarity and reflection's congruence, but if we put a similarity transformation and a congruence transformation together, we end up with a similarity transformation. Right? It's going to be dilated and then reflected. So that means our figures are similar, and A, B, C, D is similar to E, F, G, H. And in the same place that you saw this podcast will be some whiteboard practice problems for you to practice and in some innovative new ways, I hope. All right, so bye for now.